Hello, and thank you for joining my talk today. I just wanted to go over a quick, brief introduction of myself and the company, and then I'll move into more of the technical presentation. So my name is Katie Hahn. I'm a business development engineer at Kayaku Advanced Materials, also known as CAM. We're located in Westborough, Massachusetts. We're formerly known as Microchem Corporation, which you may know, and we're a chemical manufacturer of specialty chemicals for MEMS, microelectronics, in semiconductor device packaging. So today I'll be going over the progression in a novel low-loss photodielectric for wafer level packaging. If you attended ECTC in 2020, you would have seen my paper and technical presentation then. However, if you do want to go back and just do a debrief, you can go to our website under the news tab and publications, and you can access my paper there. So quick overview, I'll first go over the background and motivation of the project, and then get into kind of the new property evaluations and reliability testings we've completed since last year, and then some key takeaways. As we head into the fourth industrial revolution, or Industry 4.0, there's a push for interconnectedness of technology and their effect on people and processes, driving a more efficient and productive world. So a few notable megatrends driving this era are 6G communications, IoT, augmented and virtual reality, and automation. So from a device standpoint, the requirements are really asking for higher bandwidth, lower power consumption, high functionality, more memory and sensors, lower latency, all while further miniaturizing the system. So these extreme requirements are really what enables the need for advanced packaging or heterogeneous integration. So the electronics industry relies on the integration of separately manufactured components into higher level assemblies to enable enhanced functionality in operations. The evolution of heterogeneous packages designs creates new material requirements as these diverse components are interconnected into new packaging architectures for the multitude of industries where electronics are used. We see this opportunity arise for new dielectric materials that can mitigate some of the current challenges found with incumbent materials while still meeting reliability specifications. The performance of the end device becomes really highly dependent on the dielectric material, and I will be presenting on the progress on the material properties and reliability evaluation of PRL 29, CAM's novel ultra-low-loss dielectric material. So we've designed this material to be a liquid negative-tone spin-on dielectric with a final film thickness ranging between 5 micron to 15 micron in one single solution. The corresponding spin speed curve is displayed here on the right, and spin coating is recommended at these spin speeds ranging from 1,000 to 4,000 RPM to meet the target film thickness, and then that's followed by a 95°C soft bake for 2 minutes to bake off any residual solvent. And this specific formulation is in pygmia. So after soft baking, this material undergoes a cure step via photoinitiator to cross-link the material. We recommend a 250 millijoule per centimeter squared exposure dose for a 10 micron film thickness, and that's followed by a post-exposure bake at 110°C for 2 minutes, and this again is optimized for a 10 micron film thickness. This can obviously be optimized further for other film thicknesses, but after PEB, the wafer undergoes a development step, which is recommended at 6 minutes for immersion for a 10 micron film thickness to achieve a 1:1 aspect ratio. And then the development step will clean out any unexposed areas of the wafer. Finally, the material requires a cure step of 200°C for an hour under nitrogen to ensure a full cure. One can expect around a 4% film loss, which is between a soft bake and then after development. And then after curing the film, one can expect around 5% shrinkage, which is from development to after cure. And then this range in film thickness is really based off of dielectric material market needs, but can easily be altered in terms of dilution to meet other potential application needs. So PRL 29, like I said, achieves a 1:1 aspect ratio, and we've thus far optimized resolution for 15 micron and 10 micron film thicknesses on a broadband exposure tool with the 360 long pass filter. We've also completed a preliminary eyeline stepper evaluation to understand the change in profile with respect to focus offset. So sidewall slope is important to ensure full metal coverage and uniformity. Typically, metal redistribution layers are sputtered onto the dielectric layer. A vertical sidewall or inverted slope will lead to gaps in the metal coverage and sharp corners, creating a vector point of high stress. So therefore, it's preferred for the material to possess almost a retrograde profile. PRL 29 samples were patterned with a 4 micron focus offset step from -4 micron to +14 micron, and a hard cured to achieve around a 5 micron and 10 micron film thickness. We observed the 20 micron via profiles under SEM, and that's what's shown here. So at a 0 micron focus offset for a 10 micron film thickness, we achieve straight sidewalls. And then with the positive focus offset, the profile begins to show a positive slope, which is desirable for minimizing stresses in the device stack and to ensure a uniform RDL deposition. And then at a negative focus offset, the 10 micron fixed sample begins to develop an inverted slope, which would result in gaps in the middle layer. And this would be undesirable. So another important part for dielectric materials is adhesion, and it's an important parameter really to understand the behavior of the material to metals or other inorganic substrates it may interact with in a device. So PRL 29 was coated on various metal, inorganic and organic substrates, processed through soft bake, exposure, PEB development, and cure. So the material, as you can see on the left schematic, was patterned to achieve 100 micron by 100 micron post structures at around a 15 micron film thickness. And then these structures were tested on our Dage 4000 shear tool. So shown here is a schematic and initial shear adhesion values after cure. And then later on in this presentation, I will show how the adhesion is affected by pressure cooker testing. But overall, PRL 29 exhibits good adhesion on various substrates. Mechanical properties are important to understand the inherent characteristics of materials and the way it should behave to different environments. So for example, elongation is a good indication of passing thermal cycling and drop tests. In last year's presentation, we reviewed the material's modulus at different temperatures to simulate a thermal cycling environment. Additionally, we showed the mechanical properties after a series of high temperature testing. Something we noticed during the development process of this material was that there really is no across-the-board standard for measuring elongation. Therefore, it's kind of difficult to compare different material type mechanical properties and to be able to benchmark them. So I want to go through the process that we developed at CAM to measure the mechanical properties of our permanent resists. So here we have a coated wafer with the desired resist. For us, it was PRL 29. And we coated that to a 15 micron film thickness. After soft bake, a rectangle freestanding film negative mask was used to expose and develop out the samples. After development in the cure step, the freestanding films were etched off of silicon wafer or the desired substrate. And now our samples are really ready to test. And what's not shown here in this final schematic is that we actually use an additional holder to help aid the difficult process of aligning the fragile film onto the instron before testing. So each of these films are around 100 millimeter long by 10 micron wide. And we use, or 10 millimeter wide, we use a 50 millimeter gap and pull at a 50 millimeter per minute rate to measure the mechanical properties. As you can see, the process is probably the most difficult and tedious part out of everything, which really leads to high variability, and especially our elongation values. You know, any slight misalignment onto the instron or any defect in the film will lead to permanent break or premature break. So with that, let's take a look at some of the new data we've generated regarding the effect of cure temperature and time on mechanical properties. So we know that customers using dielectric materials may have their own methods of curing due to just pre-existing process requirements. Here we have tested different cure temperatures for PRL 29 at 200 degrees C and 250 degrees C, and then different durations at 60 minutes, 90 minutes, and then 120 minutes. Then we measure the mechanical properties for each cure. And based on our results, we can conclude that there is no significant effect on tensile strength, and that the Young's modulus slightly increases from 1.6 gigapascals to around 2 gigapascals, above 250 degrees C for a 90-minute cure. As we discussed in the previous slide, the elongation values have high variability. So at the bottom chart, inside the blue bars is the average of the samples with an average sample size of around 5 test specimens. The orange dot above the blue bar is the maximum value or elongation max achieved per sample set. So it's really difficult to make a conclusion from the results as the deviation is quite high. However, we can maybe say that the elongation decreases with increasing temperature from 200 degrees to 250 degrees C. However, overall, PRL-29 is capable of being cured at a wide range of temperatures and durations while maintaining a good balance of mechanical properties. So let's get into reliability testing. Going back to the shear adhesion performance, we tested after running test wafers through the pressure cooker testing, and we checked adhesion after 48 hours and then again after 96 hours of PCT. So this was run at 121 degrees C at 100% relative humidity at 2 atmospheric pressure. And here's the results that we've plotted. So to compare the baseline in blue with the PCT results in orange for 48 and gray for 96 hours, overall the adhesion of the material did not go below the threshold of what we consider poor adhesion. I do want to note that the significant drop in copper adhesion after 96 hours is probably due to the copper substrate just oxidizing itself. When we tested the PRL-29 on copper using the crosshatch tape peel test after PCT, the material did pass. So I think that's what this is showing. And then it's important to have a good understanding of how the material will behave after reliability testing. So I've tabulated the mechanical properties of PRL-29 after PCT, thermal cycling, and high temperature stability in comparison to the baseline after being cured for 200 degrees C for an hour. So after PCT and TCT for 1,000 cycles, the material properties don't change significantly. I would even argue that TCT for 2,000 cycles isn't super significant either. High temperature stability testing is extremely harsh conditions, and we see after 225 degrees C and 200 degrees C for 24 hours of testing under air, the material does become more brittle, and this is really a result of PRL-29's oxidative stability. However, the material will likely be in a sealed package, unexposed to air, and so to simulate this in-package environment, we ran the test under nitrogen. As seen in this table, the material properties do not begin to degrade as under air. So temperature cycling was also completed with photo pattern structures, really to test the CTE mismatch and overall resistance of the material to exposure of extreme temperatures. Thermal mismatch of polymer to substrate or metal can cause stress-induced failure, such as solder joint cracking, warpage, or delamination. PRL-29 has a CTE of around 60 ppm per C, compared to silicon, which is around 26. So to offset this value, PRL-29 has a low internal residual stress value of around 14 megapascals, along with that good balance of mechanical properties as we've already proved previously. So a 15 micron thick film was photo patterned using an in-house stress mask on silicon wafers to create this bow tie structure with gap distances ranging from 10 micron all the way up to 300 micron. You can see some of those examples here. Temperature cycling testing was completed ranging from negative 55 degrees C to positive 125 degrees C for 2,000 cycles. And PRL-29 successfully passed all 2,000 cycles. No cracking or delamination of the film was observed. So the dielectric properties of the film are really important for 5G millimeter wave rollout and even 6G communications, which is in talks currently. This is a huge need for low-loss dielectric materials and more specifically reliable ones. Here's a graph depicting different types of polymers currently in the market in comparison to PRL-29. The DF values were measured at 3 different cure temperatures, 150 degrees C, 200, and 250 degrees C. And this was all measured at around a 20 gigahertz frequency resonator. So at 150 degrees cure, epoxy's DF value jumps over 3x its value at 200 degrees C, and it's unmeasurable at 250 degrees C due to its inability to withstand high temperatures. On the other hand, we have polyimide, which is unmeasurable at 150 degrees C because it needs that high temperature curing mechanism. And we see a 33% difference in DF value curing at 200 to 250 degrees C. Aryl alkyl thermosets are relatively stable polymers with low cure temperatures, but they're unable to cure at high temperatures. Finally, we have PRL29's DF that is stable across a wide range of temperatures from 150 to 250 without a change in the DF value. So this really gives processors a large operating window and ability to trust the stability of the polymer. Understanding the thermal stability of the material is also important for high temperature process steps and applications. For example, solder reflow steps require a preheat, soak, and reflow step where the peak temperature can reach up to 260 C all the way to 300. So it's crucial to understand the chemical components coming off at elevated temperatures and at when. So a thick film was created at CAM and outsourced to NETCH for TGA GCMS testing. The film dimensions were 4 millimeters in length by 4 millimeters in width and 1.5 millimeters thick. The test was ramped to 420 degrees C at 10 K per minute. PRL29 had around 1.4% weight loss at 400 degrees C. However, some of the initial weight loss in the beginning is believed to be residual solvent left in the film. Since the film was so thick, 1.5 millimeter film thickness is not within the operating range PRL29 is designed for. Additionally, a solder reflow check was completed in-house to ensure no failure mechanisms occurred, such as cracking, delamination, or critical dimension changes during the simulation. 100 micron by 100 micron pillar samples at 10 or 11 micron and 7 micron film thicknesses were cured at 200 degrees C for an hour under nitrogen. The samples were then exposed to a 320 degrees C peak for 10 seconds, followed by 250 degrees C soak for 2 minutes. And we were able to take SEM images between each step. So here's a film at around 10 micron without any cracking or delamination or CD changes. And then here is the film at 7 micron, also without any failure mechanisms. So overall, PRL29 was able to withstand a simulated solder reflow test. Wrapping everything up, next generation device integration requires advanced packages that aim to decrease costs, increase performance, and add functionality through integration. Additionally, market trends are pushing for smaller form factors. RDL technology really addresses this need for utilizing array area by rerouting the I/O layout. However, this technology is not feasible without insulating dielectric layers. So PRL29 is a novel insulative polymeric material with a balance of properties, allowing it to withstand harsh reliability testing environments while achieving good lithographic performance. It is proven to have robust mechanical and dielectric properties at different cure temperatures and durations. And finally, although this material is offered as a dielectric material, we believe that there is opportunity for other applications for creative use. Industry 4.0 is really not possible without innovation, and novel materials are the foundation for creating a great device. So please don't hesitate to reach out if there are any questions, comments, or interest in the material. We're currently looking for evaluation partners, and we really look forward to hearing from you. So thank you.